The Best of Our Knowledge explores topics on learning, education, and research. Coming up, scientists say recent publications by the MICrONS project are a watershed moment for neuroscience. I'll speak with David Markowitz, who coordinated the effort to develop the most advanced 3D map of neuronal circuitry ever. I'm Lucas Willard, host of The Best of Our Knowledge. This is The Best of Our Knowledge. I'm Lucas Willard. Scientists say they have made a major advancement in understanding and mapping circuitry in the brain. A years-long federally funded effort called the MICrONS project, Machine Intelligence from Cortical Networks, sought to use high-tech mapping tools and algorithms to reveal the structure of the brain's neural circuitry. An extensive package of papers was published in the journals Nature and Nature Methods, and offers a detailed map of the cellular structure of a portion of a mouse's brain. Artificial intelligence was used to trace the neural networks, and an interactive tool allows users to view a 3D visualization of the data. A portion of the brain tissue, about the size of a chia seed, contains about 84,000 neurons, 500 million synapses, and about 5.4 kilometers of neuronal wiring. Scientists say the high-resolution mapping of a tiny part of the brain allows researchers to learn more about how the brain is organized and how brain cells work together. To learn more about the MICrONS project and the team of scientists who made the effort possible, I spoke with Dr. David Markowitz, who coordinated the effort. Markowitz is a former program manager at IARPA, or the International Advanced Research Projects Activity, an organization within the Office of the Director of National Intelligence.
The origins of this program go back to the 1970s, when neuroscientists and the broader biology community began to dream about systematically unpacking intelligence. And one of the co-discoverers of the structure of DNA, Francis Crick, openly opined in an essay that it seemed impossible, this idea of unpacking all the connectivity and understanding the circuits in just a cubic millimeter of the brain, which is the size of a grain of sand. Now, in the early 1980s, a scientist at Columbia named Sidney Brenner generated the first connectome, which was a map of circuits in a worm. Really just 302 neurons, and I think they only reconstructed just the anterior or the front half of that nervous system. But it took a decade of painstaking work analyzing electron microscopy imagery. But that was like the very first hint that it might be possible to know what's now called a connectome, which is a map of the connectivity of a brain. In the late 90s and early 2000s, there was this Cambrian explosion of new technologies that were developed in neuroscience, both to record the physiology of neurons, to monitor their activity at scale, as well as to begin to look at their structure and connectivity at scale as well. When I was a graduate student at Princeton in the early 2000s, I had this harebrained idea that I was going to map the structure and the function of a complete circuit in a vertebrate. And I actually convinced the federal government, the Department of Energy, to give me the first ever grant that the US government gave for what's now called connectomics. And my project failed miserably. I learned in every possible way that you could as a graduate student how not to do this, how inadequately resourced I, as one graduate student, was. And it taught me that you were going to need a team of hundreds of people and a decade potentially of work to crack this nut. In 2013, then President Obama announced the BRAIN Initiative, which was a large-scale, focused US federal government investment in developing transformational tools and technologies to advance neuroscience. And as part of the BRAIN Initiative, the US intelligence community, which has a high-risk research arm called IARPA, created in the mold of its larger, older sibling, DARPA, IARPA decided we are going to advance our understanding of intelligence through neuroscience. And so they committed, we're going to put $100 million into studying intelligence in large-scale circuits in the brain. They found me. They said, we've heard that you have tried this before. Would you like to help us take a crack at this problem? And so that's how I left academia and went into public service for nearly a decade. And so my role was to help conceive and design the MICrONS program. And for the duration of its lifetime, I actively managed it as the federal government's program manager at IARPA.
Where did you start to put the pieces back together when digging back into this research? Where were the stumbling blocks that you had encountered maybe a decade beforehand?
I'll preface this by saying that when the general public hears about a major new scientific achievement that's been published in a high-profile journal like Nature and is getting picked up by by major news media, it's just kind of taken as obvious, like the scientists did this amazing thing, and very rarely does the conversation focus on how it came to be. Architecting big science well is essential to its success. It was essential to the Human Genome Project. It was essential to the design of the execution of the James Webb Space Telescope, and it was essential for the success of the MICrONS program. One of the So what I brought to the table as the program manager of the MICrONS program was I knew all of those ingredients that were going to be necessary and actively coordinated in tandem for this program to succeed, because I had tried and failed to do it as a graduate student a decade before. And so we knew that we would need the best in class of physiologists who could record from brains at scale. We would need the world's best anatomists who could build instrumentation to gather large-scale structural imaging data so that we could view complete neural circuits at this millimeter scale. And we knew that we would need computer scientists and data scientists who could integrate those multimodal data at a scale that had never been attempted before in neuroscience to give us something that was more than the sum of its parts. When we designed the MICrONS program, IARPA put out a solicitation. This is how we are architecting the program. These are the key pieces that we need to fit together. Give us your best ideas. And the team that ultimately succeeded in executing this vision actually proposed as 3 separate teams. And we took the best of breed from those 3 separate proposals, and we made strange bedfellows of this team from the Baylor College of Medicine, from the Allen Institute for Brain Science, and from my alma mater, Princeton University. And they had no history of prior collaboration, but we said, we're all going to work together. The government is going to actively coordinate your execution to make sure that everything goes swimmingly. I and my team met with them every 2 weeks for 5 years. We did site visits. We had a special team of testing and evaluation staff that were retained by the government to track progress and help with course corrections. So the key ingredients that we needed, other than physiology, anatomy, and data science, was computation. This is the largest multimodal data set I think that's ever been produced in biology. Just the structural data alone are 1.6 petabytes, and that's roughly 1,600 laptops worth of data storage. But our vision for this program was to make it available for collaborative analysis by the global scientific community. So we had to put it in the cloud. We worked in partnership with Google Cloud and Amazon Web Services to make this available as a public data resource. As soon as we had the data, we put it out there publicly. So although you are just now hearing about these publications that just came out in April of 2025, these data have been publicly available for nearly 4 years and it's now the most actively used neuroscience data set in the world. There are hundreds of labs that use it. So we needed high performance computing resources. We needed large scale global data sharing resources. And the final piece of the puzzle is we needed sustained support for collaborative analysis. And so that is where IARPA's role in generating this transformational data set transitioned into NIH's sustained support for these researchers that enabled the completion of the analysis and the science that was just reported on in Nature. IARPA's role was help produce the data, put it out there for the world, de-risk the premise that we can now do this new type of neuroscience at scale. And then once it had been de-risked, NIH stepped in and provided sustained funding. So this was a very rare and precious thing, just from a funding ecosystem standpoint, where we had this rare collaboration between funding agencies that are institutionally positioned to take on different levels of risk and to provide sustained funding over different timescales.
I wanted so much about the MICrONS program and what this means for science and everything, but I also cannot get out of my head as we're talking about funding and the importance of sustained investment and commitment from public agencies to compare this to what we're seeing right now within the scientific research community and cuts to federal agencies in the U.S. I don't know how much you want to spend on that topic, but it seems like the kinds of cuts that are being advocated for right now at the top of federal government would make research and progress like this impossible.
Disease does not care about your political ideology. You get sick regardless of where you fall on the political spectrum. And biomedical research should be a bipartisan issue. It's something that affects everybody. We all know somebody who's been affected by Alzheimer's disease. We all know somebody who's been affected by cancer. And if we want to solve these huge societal scale medical problems within our lifetimes, biomedical research and development can't be politicized.
You're listening to The Best of Our Knowledge. I'm Lucas Willard. If you're just joining us, I'm speaking with Dr. David Markowitz, a former program manager at IARPA. Dr. Markowitz coordinated efforts under the MICrONS project to map the neural networks of a portion of a mouse's brain. Papers published in Nature and Nature Methods and an interactive 3D mapping tool allow anyone to view the largest wiring diagram of the brain ever developed. And now back to our conversation. So back to the MICrONS project now, and with this data that has existed for years, but it seems like there needed to be time for the funding and for the technology to advance to be able to crunch the numbers, if you will. I've looked at the tool and the visualization of the neurons and the mapping, and it's so interactive. And I wonder now if you could tell me a little bit about the goal in creating the interactivity of this program and the ability for users to actually see a visual representation of all of this data that took so long to put together.
There's a lot to unpack there. IARPA's original goal in the MICrONS program was to revolutionize intelligence science. We knew that we would need this enabling data resource. We knew that we would need to make it available to researchers. And I knew when I came to IARPA that I had a fixed window of time to actively support this endeavor, which was 5 years of funding. That's how long ARPA programs typically last. But I also knew as a neuroscientist that this would be a data set that would provide enduring value for driving advances in our understanding of intelligence for a decade, potentially even longer. So we needed to make the data publicly available as soon as possible to as many researchers as possible, and make it as easy to work with the data as possible so that we could maximize our shots on goal for deriving the sorts of insights about computation and intelligence that we wanted to get on a fixed timescale. So I made it my priority from day one of the program that as soon as these data were available, we were going to put them out there so that a high school student in rural Missouri would have the same level of opportunity to make a discovery in these data as a tenured full professor at Harvard University. And so that's what we did about 4 years ago. As soon as the initial revision of the data were available, we put them out there. But your question gets at a really foundational problem in collaborative big science that cuts across disciplines, which is how do you make data not just accessible, but usable, analyzable, without requiring massive amounts of time investment in tool development and skill development. We live in a very special time right now where in the field of machine learning and AI, there's been this, again, I overuse this word, but Cambrian explosion of tools that just lower barriers for people to work with everybody else's data as quickly as possible. And so we drew on some of those best principles from the field of data science and AI. And in fact, the MICrONS program benefited greatly from work by researchers at Google who developed this visualization tool called NeuroGlancer, which is what enables you and anybody else to go into your web browser and immediately begin visualizing the fine tendrilled structure of neurons and the long-range connectivity of large-scale circuits in your web browser without knowing anything about neuroscience. And once you've solved that problem, doing deeper level analyses that require a bit more sophistication and scientific training, it's much easier for everybody. So part of my contribution as the program manager at IARPA for the MICrONS program was we set requirements for data accessibility. We had this back-end data sharing infrastructure, which was called the Neural Data Access System. It defined ways for people to connect your computer with the computers in the cloud to access specific pieces of information about this massive multi-petabyte data set. And that's enabled the development of this entire stack of tools that unlocked these scientific advances that were just reported in Nature.
Now that we have this incredible 3D mapping program that is accessible, it is interactive, and it is available to anybody who wants to click on and use it. Now that we have an actual visualization of neural connections, how can that be applied when doing research on things like Alzheimer's disease?
That is the trillion-dollar question. And I'm not being hyperbolic, because the potential of next-generation neuroscience tools and data sets to drive economic impact in AI as well as the biomedical science discipline, it cannot be overstated. And the question that you asked about how do we translate this revolutionary data resource into some meaningful insights that are actionable, people ask that exact same question when the first human genome was sequenced. What do we do with this? We have this amazing thing, great, what do we do with it? And history tells us that it took decades for people to truly understand how to work with this new type of data. You had to build an entire field of genomic science. And there were many offshoots of that have touched diverse industries from diagnostics to gene editing therapeutics to really sci-fi things like DNA data storage, which is another area in which I ran programs at IARPA. And so for transformational neuroscience data sets like MICrONS, we are in the process of building new science that will allow us to fulfill that translational vision where we can take insights about computation, insights about the pathophysiology of disease, and translate that into actionable insights for computing, for AI, and for medicine.
So it may be that one day, in addition to right now being able to visualize a part of a brain of a mouse, that we could actually, by just looking at a small part of someone's brain, possibly be able to find the parts of the brain that are in visualization not communicating with each other. Is this possibly a future evolution of this technology?
The short answer is yes. The longer answer is there are so many avenues that are now available to us because of these advances in neuroscience for diagnosing disease. And I'll throw some out there, some of which might make people feel a little bit uncomfortable. So on the more reasonable side is using data from postmortem brains, people who have donated their brains after they pass away, and we know that they have certain diseases. We can use brain mapping tools to identify how the structure of their neural circuits differs from those in healthy controls. And then through non-invasive imaging approaches in patients who are undergoing a diagnostic procedure, you can maybe register what you are seeing non-invasively from a live patient to something that's been mapped in postmortem tissue. And you can say, well, my patient's brain looks more like this early stage Alzheimer's brain, or this early stage Parkinson's brain, or this pre-symptomatic schizophrenia brain. I'm just shooting from the hip here. Another vision of how we might use these tools to aid in diagnostics in the future is actually through brain biopsy. You have 100 million neurons in your brain. You could probably do without about 20,000 of them. And so if you're a person who is experiencing symptoms and your doctor wants to make an informed diagnosis based on more than just a behavioral phenotype, there are tools now for doing very, very small extractions of a very small amount of tissue that you could then put through a neural circuit reconstruction pipeline, including mapping all of the proteins and everything else to unambiguously subtype what type of disease and what subtype this person has. And that may aid in more targeted treatments. And that's a little bit outside a lot of people's comfort zone right now. I'm not sure even I would be comfortable getting a brain biopsy today, but that's the sort of thing at the extreme that these tools could enable.
What are your hopes for the immediate future and immediate next steps for how this data will be visualized and utilized and put into potential practice by researchers around the globe? What are your hopes for the program?
I can tell you that my goal when we were undertaking the hard work of MICrONS was to lower barriers to accessing transformational data sets that didn't exist and weren't available to the community previously. We've achieved that goal now, where anybody from somebody in rural Missouri to the top tier research university has the same level of access to this rich, large-scale, multimodal neuroscience data set, really the most complex data set ever collected in neuroscience. My goal for the future, what I hope most, is that more people will feel empowered to work with the data, that more people will be inspired to pursue careers in neuroscience and to commit themselves to collecting more data sets that focus on problems that they care about, from explicitly studying disease to studying computation at even larger scale in the brain. But that requires resources. That requires institutional support. I think that there is a very real risk of cutting the impact of this $100 million government investment off at the knees if the community that is now so easily able to access the data and the tools are not empowered with the financial resources and institutional support that's needed to realize the potential of this inflection point in neuroscience. One thing I want to mention is that just by investing in basic research, just by investing in this really ambitious neuroscience program of tool development, data collection, and analysis, the MICrONS program has catalyzed a massive return on the government's investment. For that $100 million that we spent, we spun out 12 companies that collectively raised over $200 million and have driven over $400 million worth of exits, of sales of the companies. So that's driving 2x the government's investment in economic activity and 2 to 4x of the government's investment in GDP. And many studies have estimated that the impact of the Human Genome Project is anywhere from 100% to 200% of what the government spent on it. MICrONS is already exceeding that. And so what I hope is that we continue to drive this type of economic impact so that policymakers will see that when you take big swings on the hardest and most important scientific problems, it pays off for the American taxpayer.
Dr. David Markowitz is a former program manager at IARPA, or the International Advanced Research Projects Activity, an organization within the Office of the Director of National Intelligence. Markowitz coordinated efforts under the MICrONS project to map a portion of a mouse's brain that he is calling a watershed moment for neuroscience. The findings of the MICrONS project, including an interactive 3D visualization, were published in the journals Nature and Nature Methods. You're listening to The Best of Our Knowledge. I'm Lucas Willard. If you'd like to tell The Best of Our Knowledge what you think, send us an email at knowledge@wamc.org. If you want to catch up on past episodes or hear more WAMC National Productions programs on the news, academic study, books, women's issues, the media, and the environment, visit WAMCpodcasts.org. This has been The Best of Our Knowledge, episode 1804. The Best of Our Knowledge is a national production of WAMC Northeast Public Radio. Thanks to associate producer Madeline Reynolds. The latest on all National Productions programs is available via the Airwaves newsletter and our flagship station's website, WAMC.org. Until next time, I'm Lucas Willard.